In the last lecture, we were talking about the physical mechanisms of heat transfer, and we began by talking about conduction. So what we're going to do in this lecture is we're going to move into the second mode of heat transfer that we discussed, and that is convection. So if you recall, last time we said that convective heat transfer involves a fluid, be it a gas or a liquid, over some surface. And what we're looking at here, we're talking both about the random motion in the fluid, and we looked at that with conduction, and we talked about kinetic theory of gases and the fact that a gas or a liquid, the molecules are in motion. But it also involves a bulk or macroscopic motion of the fluid. And so we'll take a look at that with a schematic. And what we'll begin with is by showing the case of a flat plate where we have a fluid flowing over that flat plate. So imagine we have a flat plate and we have a fluid flowing over that plate, and it is moving from left to the right as shown here. Now what happens is we have what we call the no slip condition at the wall, and that's where we will have zero velocity along the wall, and that's why in this sketch I have shown the velocity going to zero at the wall, and then when we move away from the wall we get into what we call the free stream region, and that is outside of the hydrodynamic boundary layer. And outside of the hydrodynamic boundary layer, the velocity returns to what we call the free stream velocity, so U infinity. And so the presence of the wall is not being felt further away from the wall outside of the boundary layer. And in a like manner, we also have a thermal boundary layer, and we go from the temperature of the wall, at the wall, and this would be a case where we have a heated surface because the temperature of the wall is higher than that of the surroundings. And then as we go out of the thermal boundary layer, we then return to the condition of having T infinities. That would be the free stream temperature. And so this particular instance that we're looking at here, and this here is the temperature distribution. But this would be a case where we would have heat transfer. Given the wall is hotter than the fluid, the heat transfer or the flux is going to be moving away from the wall, and it's going to be going in that direction there. So in this particular case, what we have is we have U of y is our hydrodynamic velocity boundary layer, and T of y is our thermal boundary layer. So those are the boundary layers. If you want more information on that, you can go and watch my introductory fluid mechanics course where I go into a lot of detail about the boundary layer. Typically for isothermal flows, however, so I usually don't look at cases where there's temperature variability. In heat transfer, we always have temperature variability in the boundary layer, and that's why we have this thermal boundary layer as well. And depending upon the Prandtl number, the boundary layer, be it the hydrodynamic or the thermal boundary layer, can grow at different rates. And so a fluid with a Prandtl number of 1, they would grow at the same, and we'll talk about the Prandtl number later on in this course. But if it's 1, then they'll grow at the same rate, and if it's different than 1, then they're not growing at the same rate. So you could have a thicker hydrodynamic boundary layer versus the thermal, or the other way around. You could have a thick hydrodynamic. They depend on the Prandtl number. So when we're looking at convective heat transfer, in this course we're going to be looking at two different types of convective heat transfer, and that depends upon the forcing mechanism. And so we will talk about forced convection. So forced convection is just what it sounds like. We're forcing the fluid over the solid surface using some mechanical means. That could be a blower, it could be a pump. The surface itself could be moving, as in the case of an aircraft flying at very high elevation where the temperature would be very cold, minus 60 degrees C, and the aircraft skin would be at a higher temperature. Or we could have what we call free or natural convection. So in this course, we're going to study both of these types, forced convection as well as free convection or natural convection. And you can imagine when you have free or natural convection, if this is our wall and the fluid is moving up, the angle of the wall is going to be very important. You'll have fluid being heated, and that is what is moving it. And so there is no mechanical means that is causing the fluid to move there. But the angle becomes very important because free or natural convection at this angle is very different from free or natural convection at this angle where the fluid is moving up that way or that way versus a flat plate where you might have some free convection, but it's not going to be as strong. So anyways, we're going to look at that later on in the course. That is free or natural convection. We will also be looking at forced convection. So those are some of the concepts behind convection. Now, one of the things when we're doing convective heat transfer, another thing that we're going to be looking at is the nature in which the energy going into the fluid is being stored. And that brings up the idea of sensible and latent heat exchange. So in the case of sensible heat exchange, these are words that we've seen most likely in thermodynamics. But here the energy transfer is going into the fluid and is causing the fluid to increase in temperature. And so it's manifested in the fluid by an increase in internal energy. So if it's a gas, it would be the kinetic energy or the velocity of the gas molecules. If it's a liquid, it would be the amount that the liquid molecules are moving around. Now, latent heat exchange is another form that we will be looking at. So latent heat exchange is where the working fluid that we have in our system is going through a phase change. And typically what we'll look at in this course is going through a phase change from a liquid to a vapor and then a vapor back to a liquid. And these processes, boiling and condensation. So we've seen those and discussed them in our everyday lives, but we'll be looking at them from a technical perspective and quantifying the amount of heat transfer associated with these processes. And given that a lot of energy can go into a phase change, we'll find that the heat transfer rates for either boiling or condensation are very, very high. And I guess I should say that we could have going from a solid to a liquid as well, going through a change of state. And that would be what we call phase change materials. And sometimes those are being used in things such as solar energy, where what they'll have is a wax-like substance. It is a solid, and then when it goes into the liquid state, it absorbs a lot of energy, and that's for a thermal storage. And so that could be another application. We won't be looking at that in this course, but just be aware that phase change materials are another topic of heat transfer, and that's where you're going from solid to liquid or liquid to solid. So that is convection. What we'll be doing next is taking a look at